bottom of page 106. They define a rational function as a polynomial divided by a polynomial. And I said we're mainly going to be restricted to lines and parabolas. So look at all the different possibilities of having parabola over parabola, line over parabola, parabola over line, anything that we could think of for those. Okay? One thing I'd like you to put at the side is, I already talked about some graphs have holes. Another word for a hole is point of discontinuity. Can you see why I use the word hole? It's like only 4 letters, nice and short to write. But there has been an exam where it says, find the point of discontinuity, and if you didn't know that's a hole, that would be a problem. So, in mathematics, continuity is really important, especially in calculus. Continuity means you can draw the whole graph without lifting your pencil up. So like a parabola is continuous because I can start and draw the whole thing and I never have to lift my pencil. But a graph with a hole, you have to stop at the hole, lift up your pencil, go on the other side, and keep going. That creates a discontinuity. Asymptotes, vertical asymptotes create discontinuities because you can't draw the other side unless you lift up your pencil. Okay, characteristic number 1. What do we do with non-permissible values? And here, these are the 2 options. The 2 options for non-permissible values is they're either going to be holes or they're going to be vertical asymptotes. This apparently says vertical, and this apparently says asymptotes. If you look at it long enough, you might argue that it says nothing, but it's supposed to say holes or vertical asymptotes. So here they have a function. Can you see the non-permissible values are 3 and -1? And since those factors do not simplify and go away, that's when we have vertical asymptotes. So if we wanted to graph this one, we would have our vertical asymptotes show up here and here. Can you see that it's a parabola on the bottom and a line on the top? The degree is bigger on the bottom. This is group 3. We're not supposed to do this characteristic yet, but that's why there's an asymptote at y = 0. Whenever it's bigger on the bottom, you have a horizontal asymptote at y = 0. But then they give us a second example here where the non-permissible value is still that x can't equal 3. But in this situation, it would simplify, and after it simplifies, you get a new equation which is just x plus 1. If that happens, you have a hole. And whenever you have a hole, you figure out the coordinates of the hole. So how do I figure out the coordinates of this hole? Well, the non-permissible value was 3, so the x coordinate will definitely be 3. And then if you plug that 3 into your new simplified equation, what would you get for y? You would have got 4. So had that not been a non-permissible value, 3, 4 is a regular point on y = x plus 1. But since 3 is a non-permissible value, now it shows up as a hole, or a point of discontinuity. Here's an interesting situation I've never ever seen this on the exam. But they're like, I have a factor that cancels out. This x minus 3 would cancel out with one of the x minus 3's on the bottom. Normally when things cancel out, you get a whole, but after it cancels out, x minus 3 still shows up as a non-permissible value in the simplified equation. In that situation, you would still have a vertical asymptote. So whatever non-permissible values are in your simplified equation in the end, those will always be vertical asymptotes. Okay, with that, I'm going to get you to write down these steps. These are the 5 steps that we do every single time, no matter what the graph is, for graphing rational functions. So I'll let you write that down, and then we're done the unit. Well, we probably need to do about 10 different examples together to see how different graphs look and what different situations could come up. But basically, this is the last thing you need to learn for this unit. Our graphs together. So, steps for graphing rational functions, factor completely. Y equals x plus 5, x minus 5 over x plus 5. Step 2, list your non-permissible values. Non-permissible value, in this case, is just 1x can't equal minus 5. And will it be a whole, or will it be a vertical asymptote? Does the x plus 5 simplify? Yes. Right? So that means we are going to have a whole at negative 5 comma something. And after I simplify it, and I'm going to write this in green because it connects to the green note there, that if you have a whole, you now graph your simplified equation. I'm going to put it in a green box even. This is my simplified equation, and add the whole. Well, if this is my new equation, when x is minus 5 minus another 5, that would tell me my y coordinate is minus 10 for my whole. Okay. Note, if there's a hole in the graph, you graph the simplified equation. Is the simplified equation still a rational function? Or is it just a line? It's just y equals mx plus b now, right? We don't have to follow any more steps, because we're at that green place. We can graph this, so I'll graph it off to the side here first. How do I graph y equals x minus 5? Well, 1, 2, 3, 4, 5. That would be my y-intercept. 0, negative 5. It has a slope of 1 over 1 up 1. Probably a really good idea also to put my x-intercept of 5. And then over here, I have to add the whole to my graph at minus 5 comma minus 10. And this is why we have to do a bunch of examples with this, because example 1, we didn't even get to step 3 because once we simplified it, it no longer was a rational function. It just was a straight line with a whole added to it. Okay. Yes.
When we're drawing the hole, you want us to limit the size of the hole to like that one point?
It is just that one point. I mean, I made it really big, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Wherever that, just like you would normally put a dot, you just now make your dot with it empty in the middle.
Okay.
Okay? Not drawing a hole on the graph always loses you a whole mark. So making it a little bit bigger, exaggerated, is not a bad thing. Now it'll be 4x plus 2 over x minus 2. So now I know that in these questions they said use the equation to predict if it has vertical asymptotes. We need to practice, like, they're just going to ask you to graph stuff in the end. The textbook is slowly trying to get you to the graphing stage, but we're just going to take off the band-aid. We're graphing right from the beginning so that you can see 8 different graphing examples by the time we're done 2.4. So we have y equals 4x plus 2 over x minus 2. We would start by factoring. There's a common factor in the top. I can take out a 2. And I factor to see if anything cancels out, because my non-permissible values here, what would make you divide by 0? X can't equal 2. But in this situation, it doesn't cancel out. So last time it canceled out and we had a hole. This time we're going to have a vertical asymptote at x equals 2. So notation, because this is, I mean, you guys like to lose marks on how we write things all the time. Non-permissible values have a line through saying x can't equal something. Asymptotes are equations. They always have x equals 2. So a common mistake is someone draws an asymptote and then they write x can't equal 2 underneath, but it's an equation. It needs an equal sign. So as far as graphing, sometimes I just start, first thing I know about this graph is that I can take out my red pen and I know there's going to be a vertical asymptote at x equals 2. Since nothing canceled out, and I can maybe pull my instructions, right, so we can pretend to see them while we're doing this question. Nothing canceled out, so I don't have that green thing, right? The green thing happens only if you have a hole. You graph your new equation and graph the new. So now we're at step 3. Determine if there's horizontal asymptotes or oblique asymptotes. What group do we have? Do you see that you have a line divided by a line? And any time that it's the same on the top and the bottom, you will have a horizontal asymptote at y equals, what's the biggest degree is x. I'm going to write it as 4 over 1, and then rewrite it at y equals 4 after, because I'm showing you that I take the number in front of x on the top and the number in front of x on the bottom. So then I can go to my graph, 1, 2, 3, 4. And add that asymptote. That's step 3. Step 4. Draw all of your intercepts. I always start with the y-intercept because it's the easiest. The y-intercept you can find by looking at your original equation and plugging in 0 for x. Can you see if you plug in 0 for x, you would get a 2 in your numerator and a negative 2 in your denominator. So my y-intercept, 2 divided by negative 2 is a negative 1. I'm going to have a y-intercept at negative 1. Draw a dot there. 0, negative 1. Perfect. X-intercepts. X-intercepts are really important because an x-intercept will happen when y is equal to 0, and an x-intercept when you have a rational function. That's like having a fraction. The only way a fraction is equal to 0 is if the numerator is equal to 0. Okay? So a shortcut is I can just look at the top of my fraction and it's already factored. What makes the top equal to 0? can you see that it would be negative 1/2? So using the shortcut, your x-intercept you can find by just looking at your numerator. Okay? If you would like to do it a longer way, plug in 0 for y, and I'm going to take the factored one here, 2x plus 1 over x minus 2. Plug in 0 for y and solve. Well, how do I get rid of a fraction? I can multiply this side by x minus 2, and I can multiply this side by x minus 2. Does it make sense those x minus 2's would cancel? And since the side is 0, you just get your numerator, right? The shortcut I said is just look at your numerator. Can you see why you don't have to look at the denominator? Because when you're solving, it would just disappear. And then it's already factored, and I guess I could split it here, but only negative 1/2 would work. Because it's only one factor. The 2 is never going to equal 0. So, on my graph, I'll label that one as well. And what's really important is that after you solve for your x-intercepts, when you graph, you cannot have any more x-intercepts. If you invent new x-intercepts, you know you've done something wrong. We solve for our x-intercepts, and that is the only x-intercepts you can have. So when we look back at our steps here, in step 4, which you might have to look at your notes because it's really tiny, it says intercepts and nice points, 1 point in each section. Now we're going to talk about what that means. Every time you have a vertical asymptote, it splits your domain up into 2 different sections. We already have points in section 1, but we do not have any points in section 2. So to get a nice point, I'll even write nice point, pick an x value in section 2. Well, you can pick anything bigger than 2. I usually like to pick something close, so it's not like way off in my graph. So I'll pick 3. Sometimes 4 is nicer, but you can pick any number you want, plug that into the original equation. Can you see the bottom would be 3 minus 2? Is 1. Here, I'll just do my mental math as 2 times 3 is 6, plus 1 is 7. 7 times 2 would be 14. So, on my graph, I would go to 3, 14. Oh my goodness, move this out of the way. That is way up here. Label it. And once you have points in each section, you just need to graph towards the asymptotes. And your graph is done. So that's step 5, draw your graph towards the asymptotes. But you need at least 1 point in each section to do that. And that is a more full, all 5 steps of what you need to do. All right, you can circle question number 5, but next week we'll practice a lot more.